In this video, we're going to look at how thermal energy might move from one place to another place. We're going to look at one of the mechanisms by which heat can flow, in this case, through a solid. There are three main states of matter: solid, liquids and gases. And different heat transfer mechanisms might dominate in these different states. But for a solid, conduction is the main way in which heat might move through the material. For us to understand how this occurs, we need to understand what a solid is like on a microscopic scale. All materials are made out of atoms. If we could zoom in and see an atom, we would have to go to 10 to the minus 10 meters, a scale that is so unimaginably short that the number actually represents 1/10 billionth of a meter. Very small indeed. Smaller than an optical microscope might be able to resolve, smaller than an electron microscope might be able to see. An atom we understand to be a very small particle, and it is made up of some main parts. To start with, if this circle represented an atom, what scientists have found in the last 100 years or so is that it is not uniform. It is not a round billiard ball with no structure. In fact, in the centre, very, very small, but I'm going to draw it larger so you can see in my diagram, we have something that we refer to as the atomic nucleus. Now, the atomic nucleus is 1/10,000th of the size of the whole atom. If the atom was the size of a large football stadium, then the atomic nucleus would be about the size of a pinhead in the centre. Very small. So this diagram is representative only, it's not drawn to scale. Inside the atomic nucleus, we find some particles. Before I talk about those, a key misconception is the confusion between the atomic nucleus and the biological cell nucleus. Now, nucleus comes from the Latin, basically means the centre. In a biological cell, the nucleus is the part of that cell that contains the DNA and the reproducing equipment that the cell needs. Here, this is not in any way part of the machinery of reproducing or anything like that, because this atom is significantly smaller and not alive. The nucleus is just a little point of matter in the centre of each atom. Now, we know that the nucleus is the residing place of two subatomic particles. Now, I'm going to draw a few in here, and they are all very close together. Some of them I'm going to draw with a positive symbol on them. These are positive charges, and we give them the special name protons. They carry a positive charge. Also, in the nucleus, there are some particles that do not have any charge at all. They have a charge of 0, and these are called neutrons. And these have no charge at all. And there is one more particle that sits inside an atom, but it doesn't sit inside the nucleus. It's actually around the outside of the nucleus. And these particles sit around here, and I have drawn them with a negative symbol. They sit around the nucleus, and these are called electrons. And these carry a negative charge. Now, this isn't supposed to be a video on atomic physics, but you do need to understand this to fully understand the heat transfer mechanism of conduction. Here are some interesting facts. The electrons carry almost a negligible mass. The mass of this is about 1/2000th of the mass of one of those. So nearly all of the mass is located in the nucleus. I've said that these carry charge, and we need to just understand what charge means for a second as well. Charge is a property of a material that means it experiences forces from other charged objects. A repellent force if the other object is of the same charge, and an attractive force if the other object is of opposite charge. So the negative electrons are attracted to the nucleus because of that difference in charge. In fact, the entire nucleus is positive because it only contains positive or neutral materials. And so what I could do is I could represent the whole nucleus as a place of just very large positive charge. And around the outside, we have negative charges. This is electrically neutral. There are as many electrons carrying negative charge as there are protons in that positive nucleus. So why is this relevant for conduction? Well, we need to think about how this atom might relate to the atom next to it. See, if I had another atom and it was here, and another atom that was perhaps here and here and here, how is it that they can sit so close together? Well, the positive nuclei of each atom would not want to get too close to another positive nuclei because the repulsive force would keep them apart. However, the interaction between the two positive charges is screened slightly by the presence of negative charges in between the pair. This positive charge, using strange language, almost can't see this positive charge because there's a negative charge in the way, and they are both attracted to that negative charge. And we call that mutual attraction towards an electron between them as a chemical bond. It is what holds a molecule together. A chemical bond between these two atoms. Chemical bonds are the things that enable molecules to stick together. In any of the molecules that you might be familiar with, such as a molecule of water, the two hydrogens and the oxygen, they're held in place by the mutual attraction between those positive nuclei of the electrons that are in between. Here, another good example, CO2 and other atmospheric gases. But what about in a solid? We need to talk about solids because it is in a solid that thermal conduction takes place. The periodic table. And you can see that all of these atoms are arranged by increasing number of protons, as we'd say in physics, and increasing number of electrons, as we'd say in chemistry. You can see that all these ones in the middle are very similar to each other. They're all a metal, a shiny material. Some of them are slightly different colours, but basically they're the same. And the place where it gets really interesting is up here in this corner of the periodic table. These elements are non-metals. They're different to these, and they're different in the way that they bond together. Now, any substance that has metallic bonding has this very shiny kind of appearance. And there's a reason for that. And it's because the atoms have become very regularly arranged. Whereas in the non-metals, they are more powdery and they don't look shiny at all. And that is because the atoms are more disorganized in their arrangement. So here I have a primitive model of some metallic bonding. And you can see that each of these polystyrene balls, they represent the nucleus of an atom. And the springs in between them, they represent the bonds formed by the mutual attraction to electrons that might sit in between. And here is a key difference between an insulator and a conductor. An insulator will have those electrons quite firmly held in place between this atom and that atom, with no freedom whatsoever. Those electrons are described as localized because they can only be in one place, just here. And what happens in a metal is something quite remarkable. The electrons at the very outer edges of the atoms are actually free to move. They act like a fluid amongst this solid structure. So though the positive nuclei of the atoms remain stationary, the electrons act like a liquid flowing around through the structure, like water in a sponge. An electron here might switch position to be an electron over there, and then it might switch again to be an electron over there. We call these delocalized electrons, sometimes free electrons. And this is what makes a metal different from a non-metal, the fact that a metal has free electrons. These electrons are still associated with atoms, but not one atom. They just hang around. And this affects the thermal conductivity of a metal. So here I have a metal rod, and I suspect that this is made out of steel. If I was to heat one end of this, then what would happen is that heat would travel through the rod, and this end of the rod that is away from the source of the thermal energy would itself rise in thermal energy. Heat would have transferred through and been stored up in a place that it wasn't before. Now, why is that the case? Why in metals do we find that they have such good conduction? Well, here on the board I have drawn a picture of a metal, a representation similar to the lattice that I have in 3 dimensions on the table right here. But now what I've done is I've taken a slice to look at a single layer, and so I can represent it in 2 dimensions, a flat image on the board. And these positives I've drawn here are the white polystyrene balls that you can see on that model. They represent the atomic nuclei. They represent the middle of the atoms of whatever this substance is. And also here I've drawn some electrons, and these are the blue circles. They sit in between the positive nuclei. Now, the main thing about metals that makes them good thermal conductors is, firstly, that the atoms are in a regular arrangement. You see, the atoms being in a regular arrangement mean that if one end picks up some thermal energy, then the energy gets passed through the positive nuclei. Let me demonstrate. See here, this model is slightly flexible. The atoms can quiver and vibrate. And if it is a regular lattice like this, this shape, this construct is called a lattice. If it starts to vibrate, then it has more thermal energy than if the vibration has nearly ceased. And as it gets more and more, if I shook this too violently, then of course what would start to happen is polystyrene balls would start to come off, and you can see indeed that someone in the past has been a little bit too aggressive with this model. And in fact, that is modelling very nicely what happens when something starts to melt, that the fixed position of the atoms starts to become a little bit more flexible and they move around. So you can see having a regular lattice means that if I start vibrating it anywhere, the whole thing will start to quiver. And that is the first reason why metals are such good thermal conductors, because a high temperature in a solid can be seen as a vibration of the particles. If you're vibrating, you not only have a high temperature, but also you have stored thermal energy. And what happens is that vibration quivers through the structure to the other side and passes on the thermal energy over here. And if that was it, then nearly any substance could pass on energy. But an insulator is quite different. An insulator, unlike the metal rod, and more like this wooden stick, doesn't have this regular arrangement of atoms. The atoms are more randomly arranged. The electrons between them are more fixed in position. the insulator quite often is made of multiple different types of atoms, different elements. This wood is basically full of hydrocarbons, hydrogens, carbons, and a few other things. And the lack of having a regular arrangement, the lattice structure of a metal, means that its surface is not shiny, because its surface on a microscopic level would be as rough as the surface of the moon. Whereas a slice of metal would be so pristine, it would be almost mirror-like in its flatness, and why metals are shiny. Now, an insulator like this, not having a regular lattice, is not going to be able to very effectively allow the heat to travel along it. But there is a second reason as well, and it's to do with the electrons. In this model, if we said that this was a metal, we said the electrons were free. And here they are free. And what they can do is, if they gain some energy, they get too close to one of these quivering nuclei, and being so light, as explained earlier, they would take a little bit of that energy and convert it into their own kinetic energy. They get a little bump from a heavy atom, and they, being really light, ping off at high speed. And so these electrons would ping off and be able to move through the structure, transferring the kinetic energy that they have received on a microscopic scale, what we perceive on a larger scale as heat, to the other side of the structure. With a metal, it has free electrons, so it can do this readily. But in an insulator, the electrons are bound, involved in bonding. They can't move, and so they're not free to move through the structure. So insulators, for two reasons, are poor thermal conductors, and metals, for two reasons, are good. Thermal conductivity explains why things may burn. This wooden ruler would burn. This metal pole would not. There are chemical reasons why not, but there's a physics reason as well. If I place this metal pole at the end of a Bunsen burner and increase the thermal energy just here, then the conductivity of this metal would allow the heat to move up the structure to the other end. And so no matter what I did, I would not be able to build up enough heat in one place without it being transferred away. In an insulator, it's not able to transmit the heat through the material. So what happens is this part above the Bunsen flame gets hotter and hotter and hotter, and the heat can't escape. If the heat builds up to a certain amount, if the temperature gets to a certain value, then the wood itself can start to undergo a combustion reaction. And one final thing. If you're a good conductor of heat, you're probably a good conductor of electricity. You see, electricity is the movement of electrons through a conductor. And that also was one of the two mechanisms by which thermal energy might move through a metal. So if you've got free electrons and you can move through a metal structure, then you're probably going to also allow electrons to move through you as electrical energy transfer.